We're now going into the last session of the morning. We have two speakers kind of talking to us about metabolic health. And the first speaker is Dr. Thomas Weimbs, and as many of you actually know him, particularly from the patient community. And he had done some very interesting study looking at the effects of ketogenic diet in slowing cystic kidney disease progression. So I just want to ask Thomas to come, and thank you for coming to Toronto, Thomas.
Thank you, York, for putting this fantastic conference together and having me here. Let's see. Do I have to start a button? There we go. All right. So I would like to, let's see. So here's our beautiful campus, and my button doesn't do anything. There we go. All right. So real quick, just the disclosures. The one thing to point out is that besides my day job at UC Santa Barbara, I'm also the founder and president of Santa Barbara Nutrients. And here's our campus again. Here's my lab at UCSB. And the data that I'm going to show are mostly from Jacob Torres and Sebastian Strubel on the top left there. Just to kind of put things together or frame things, so we've been talking a lot about what are the different factors that influence the progression of polycystic kidney disease. So how do you get from a normal-looking kidney to a highly polycystic kidney, and what can we do about it? Of course, what I think yesterday we heard a lot about is pharmacological approaches. We've heard all about tolvaptan, the only drug that's currently FDA approved for polycystic kidney disease. We've heard a lot from Greg Gemino gave a great overview of other pharmacological approaches, including things like gene therapy and so on. And of course, in many of our labs, that has been sort of like at the forefront of what signaling pathways can we identify that play a role in polycystic kidney disease. How can we influence them? That is sort of like the most common approach. So what I wanted to tell you about is our research that has led us a little bit into a different direction, where we think that there are actually factors that influence the disease progression in a negative way, if you will, that make it worse. Those could be diet and lifestyle factors. And actually, Dr. Pei gave a fantastic overview yesterday about the heterogeneity of the rate of disease progression in PKD, even amongst family members that all have the same gene mutation. Dr. Pei showed some really nice data, how there appear to be modifiers that can actually be, positive or negative potentially. So what if there were factors that could be influenced by diet or lifestyle that make PKD worse? What we have worked on is something that I put in this little cloud there and call kidney stone risk, as well as metabolic disease. So kind of like very nebulous things. So I'm going to go into it a little bit more. If we would know what those factors would be that can worsen the disease progression as a conservative approach, of course, we could try to take these factors away, mitigate them, reduce them, and might be able to influence the progression of PKD progression. So, and of course, a conservative approach always would be a good thing to do with regard to medical ethics. When prevention is preferable to a cure. First, do no harm. This kind of thing. And of course, actually, in this morning session, there was some really interesting discussions about what drives our healthcare system, and a lot of the funding has to do with funding for the pharmacological approach, leaving relatively little funding over for any conservative approaches. So what I sort of broke my talk, my presentation into 4 stories. A crystal story. I'm going to talk about this second hit, third hit model that we already heard about from Terry Watnick, Greg Gemino yesterday. I'll talk about crystals, ketosis, keto in human ADPKD, and sort of our efforts to develop a lifestyle, diet and lifestyle program. As a quick reminder, so what are cysts? How do they arise? So we all know they arise out of individual renal tubule epithelial cells that start to proliferate, form these dilated tubules, eventually form cysts. And we and many others have asked, what are the underlying signaling pathways and signaling molecules, and we had focused a lot on things like mTOR, STAT3, and so on. And one question has always been, what are the kind of the triggering factors that lead to the kind of the first initiation of things? I'll have a slide in just a second on this whole third hit idea. And we had kind of come up with this idea, what if these microcrystals that I'll talk about in a second could be part of this third hit. So, okay, so what am I talking about? Second hit, third hit, first hit? Why does it even matter? Does it matter? We had already heard from Dr. Watnick yesterday the idea, of course, that a patient is a heterozygous mutant, if you will. One of the, let's say, PKD1 alleles are affected by a mutation. The other one is fine. There would be second hit somatic mutations that occur later on in life in a sort of a random fashion affecting the good allele. But if we do this in animals, in mice, and Dr. Gemino had published, a number of years ago, kind of like a groundbreaking paper showing that if you knock out in an adult mouse both alleles of PKD1, that actually nothing happens for a really long time. So it appears that a second hit by itself doesn't initially do anything. And a number of labs had then shown that if you then take this mouse and subject it to a form of renal injury, then you end up with rapid cystic initiation and cystic progression. This idea of a third hit was kind of born, suggesting that in addition to the genetic mutations, some other factor might have to occur to initiate disease progression. So that's kind of this hammer up here. And the question is, what could this hammer be? So experimentally, this has been shown that ischemia reperfusion injury can be the hammer, or nephrotoxins can be the hammer. But looking into human populations, those seem to be somewhat, rare conditions that may not be able to explain the sort of the continuous progression of polycystic kidney disease. So what is the hammer? We have had looked and published in this paper so what we think is at least one part potentially of a hammer like this. That's a paper that came out a couple of years ago in the Journal of Clinical Investigation. I call it the crystal paper. And because it's published, I'll just go over real quick what the kind of the bottom line is here. So if you start out with a normal healthy tubule with fluid flow going through it, that's the starting out situation. And as we probably all know, the kidney is constantly challenged by microcrystals that can precipitate due to the concentration of the primary urine. And in humans, these microcrystals go on to form, of course, kidney stones, macroscopic kidney stones, and the most common type are calcium oxalate, calcium phosphate, and uric acid kidney stones. But they don't start out as big stones. They start out as microcrystals in tubule humans. And these microcrystals can injure tubules, they can cause occlusion. And the question had been, how does the kidney actually deal with them, which was not really well understood. And what we found and showed in this paper is that these microcrystals, these lodged microcrystals can activate signaling pathways that happen to be actually the same signaling pathways that are also activated in polycystic kidney disease, including mTOR and STAT3. That this then leads to tubule dilation with the apparent purpose of flushing out these crystals. And in a normal kidney, once these crystals are removed and excreted, the tubule lumen is able to go back to normal, to the normal diameter. The signaling pathways are turned off again, and you would never know anything about it. So probably in all of our kidneys right now, we all have some microcrystals, and our kidneys are just dealing with them in this way. And what we found is that if you do this in animals that are preconditioned to form polycystic kidney disease, that these dilated tubules can overshoot and form cysts. So we can actually make the disease worse by challenging the kidneys with more and more of these crystals. And the way this can look like on the left is a rat model of polycystic kidney disease that we challenged with a high oxalate burden. So they form thousands of calcium oxalate microcrystals in their kidneys. I don't have the picture here right now, but one of the readouts we can always look at is, after some time, what happens to their cystic kidneys. What's plotted here is just a 2 kidney weight as a % of total body weight ratio. And you can maybe see in the challenged rats, those are the red dots, that the progression was much faster. They have worse kidney disease than those that were not challenged. And on the right hand is a different rat model of polycystic kidney disease. This experiment was actually done by Vicente Torres's group. This particular rat model was challenged with a high phosphate diet. And again, calcium phosphate is one of these insoluble compounds that can form. And you can see that this only twice the amount of phosphate in the diet already very strongly accelerated the progression of the disease in this rat model as well. Lots and lots of other data, of course, in the paper, and we looked at all the signaling pathways, at fibrosis and so on, and everything gets worse. So if we try to think of it in terms of humans, so where does oxalate actually come from? Where does phosphate come from? A lot of this comes from our diet. Oxalate is very high in certain plants, such as spinach, almonds, dark chocolate, Swiss chard, and so on. And phosphate, a very strong component of our intake, is from inorganic phosphate food additives that the food industry adds. They have no nutritional value, but they have, of course, industrial value. Potentially one could think about reducing the intake of these renal stressors. And so a little pop quiz, and I'm just going to give the answer away. So what is one of the kidney's innate defenses against calcium crystal precipitation? And the answer is actually something really simple: citrate. Citric acid, essentially, that is filtered, goes through the tubular system, and citrate has the ability to chelate calcium and prevent the formation of calcium oxalate and phosphate microcrystals, and that's one of the natural defenses of the kidneys. So the question is, could you just take citrate and supplement it in a rat model of polycystic kidney disease, and might this have any benefit? And the answer is yes. So this here shows a titration curve of just adding citrate to the drinking water in a PKD rat model. And we can see, there's a dose-dependent beneficial effect. These kidneys look way better, much fewer cysts, much less activation of signaling pathways, and so on. And that's has actually been known for over 2 decades that citrate therapy is highly beneficial. It wasn't understood back then when it was published by another investigator what the mechanism could be. And this was never followed up with any clinical trials and was never really further explored. So What we looked at, and that's also part of this crystal paper, is in patients, in ADPKD patients, we asked, does the urinary citrate level possibly associate with disease progression? And we see this inverse relationship, essentially meaning the lower the urinary citrate level is, or the more hypocitraturia patients have, the worse they typically are. And this, correlates well with many other aspects in the clinical literature. Patients with ADPKD are known to have an abnormally low urine pH, which leads to hypocitraturia that predisposes to a higher risk for forming kidney stones. And indeed, patients with kidney stones have a much higher risk. And those patients with kidney stones also have a faster progression of their polycystic kidney disease. There's a strong association with uric acid as well. High uric acid levels are very common in PKD, and those patients with higher uric acid levels have, again, faster progression. So this all seemed to make sense. So the question is, which dietary factors may worsen progression of polycystic kidney disease? So we would argue that oxalate is one of those factors, forming calcium oxalate, microcrystals, and kidney stones. Another factor would be high phosphate intake leading to calcium phosphate burden in the kidney. And we wondered about the third one, uric acid. So what about uric acid, which is also very common in PKD patients? So this is something that's not published yet, and I'm only going to go through, due to lack of time, we just show a couple of highlights here. So we have taken, again, in this experiment, just wild-type rats, normal rats, challenged them with high uric acid in the diet. And in rats, you have to inhibit an enzyme that we humans have lost in evolution. That's uricase, which normally degrades uric acid. If you do this, you can very easily, have a high uric acid burden leading to uric acid microcrystals in those kidneys, and you can maybe appreciate the tubal dilation that is going on, and that's also quantified here. If you do a washout, in this case a 4-week washout, everything goes back to normal. The microcrystals are gone. The tubal diameters go back to normal. What we also see is essentially the same activation of numerous signaling pathways. So on the top, we see, looking at KIM1, kidney injury marker, you see there's barely anything in the control. It lights up like a Christmas tree in the uric acid challenge. And you can see all these dilated tubules are highly positive. And again, after the washout, it goes away. And the same is true for anything else we have looked at STAT3 or mTOR in this case. So what if we challenge a PKD rat model with high uric acid? We've done this here, and this is looking at the hen rat model. You can maybe see that after the uric acid challenge, there was actually a much faster progression of the disease. And again, we can quantify this any number of ways, by looking at the cystic index, cyst number, or even serum creatinine as a readout of renal function. So we know now how to worsen the disease. How about an orthologous rat model? So the previous one was a non-orthologous rat model. And there hasn't really been an orthologous rat model. So there's of course plenty of orthologous mouse models. But Peter Harris at the Mayo Clinic actually made a rat model, just a straight knockout of the PKD1 gene, which turned out to be not very useful in the experiments I think he was planning to do with it, because the heterozygous animal essentially had no phenotype, just exactly like in mice. So they don't form any cysts. They have normal kidneys. And of course, the homozygous rats are embryonically lethal. Again, nothing you can really do with them. So I asked Peter to send us those rats, please, which he did very kindly. And we thought, okay, what if we take those heterozygous rats, which genotypically are essentially the same as a heterozygous PKD patient. And what if we just challenge them with uric acid? So we did this, and here are the results. So in this case, we challenged them for 4 weeks, again with uric acid in the diet. We have a 4-week washout, and this actually triggered polycystic kidney disease in these heterozygous rats, but that normally don't form polycystic kidneys. So you can see maybe on the right-hand kidney there, those challenged, cystic kidneys. We can look at all kinds of different parameters. And we found this very, very interesting because until this point, it had thought that a heterozygous animal doesn't actually form polycystic kidney disease. But apparently, if you just challenge them with the correct challenge, you can trigger polycystic kidney disease in them. So this led us to a little bit of a modification of this third hit mechanism. So up there on the top is the same third hit mechanism I told you about before. And we think those data might suggest that you may not necessarily always need a second hit somatic mutation, that even a heterozygous renal cell, if the hammer is correct, so to speak, if the challenge is correct, that this can lead to cyst formation and with potentially very important implications for patients, because patients are essentially these heterozygous folks, walking around with one germline mutation. All right, so we would add to our list of renal stressors that can worsen PKD progression. Besides oxalate and phosphate, we would add uric acid to the list. And if we think about it in terms of, in this conservative approach kind of scheme, what would this potentially mean for patients? So I filled in a few things in this kidney stone risk cloud there, what one could do about reducing this risk. That would be, reducing the intake of oxalate, inorganic phosphate, or uric acid precursors such as purines in meat. Normalizing the urine pH, which is usually aberrantly low in PKD. Normalizing urine citrate levels, which again are, it's usually too low in patients with PKD. And potentially switching to more plant-focused diets, which are more alkalinizing and again reducing the risk for kidney stone formation. So, all right. Keep this in mind for a second, and let me switch over to the kind of like the other cloud here, the metabolic disease cloud. This relates to this other paper we also published a couple of years ago, again with Jacob Torres as the first author, where we looked into the whole metabolic angle. And this metabolic angle comes from a large number of labs that have done fantastic research. And sort of the bottom line of this is that really PKD could be considered as a metabolic disease, at least on a cellular level. And we've heard yesterday already in the talks about the Warburg mechanism, the Warburg effect playing a role in polycystic kidney disease, where these cyst-lining epithelial cells become metabolically inflexible, start depending on glucose and glycolysis as their energy sources, and essentially neglect anything where you need functioning mitochondria for. All right. So one sort of crazy experiment that led us in this direction was when a grad student in the lab decided he wanted to influence the mTOR pathway in our mice with PKD. And he did this by saying, okay, mTOR is controlled in part by the nutrient status and energy status of cells. Let me just feed my mice less food. All right, so he didn't ask me. I would have said this will never work. Luckily he didn't ask me, and he did it anyway. And he put these mice, an autologous PKD1 mouse model, on a reduced food intake regimen, a very mild reduction of food intake, only 23% reduction, and came back to me and said, hey, I did this experiment, the mice were fine, no effect on body weight gain, they're completely healthy, but one thing was very different, which is that these kidneys grew a lot less, so much less cystic progression if you put them on a reduced food intake regimen. So we published this paper saying, hey, we have no idea why, but this works. And at the same time, a group at the Mayo Clinic, including Representative Torres, had done a similar crazy experiment. I'm sure they had much better reasons for actually thinking about doing it, and had the same result. If you reduce the food intake in a couple of different PKD mouse models, and they even went down to only 10% food reduction, it has a dramatic effect on cystic progression. So since then we try to figure out why does this actually work? What does the reduced food intake actually do? And it boiled down to inducing the metabolic state of ketosis. And let me real quick recap what is ketosis even. So in this slide, it shows what not ketosis is. The way we Americans typically go about our day, we're eating from early morning to late at night and many snacks in between. So our bodies actually run on blood sugar. The cells in our body primarily metabolize glucose that feeds our cells and tissues and organs. And all of the excess of glucose that we take in is converted to fat, deposited into the adipose tissue that makes us overweight and obese. The opposite of that is, if we're under carbohydrate restriction or fasting conditions, where glucose becomes much more limiting, glucose levels go down, glucose spikes go away, insulin spikes go away, and that triggers to the adipose tissue to now tap into our fat reserves, mobilize those fatty acids, which can then become an energy source for our cells and tissues. And some of the fatty acids are converted by the liver into ketones, which is where the name ketosis comes from. The main ketone is actually, it's called beta-hydroxybutyrate, or BHB for short. And these ketones and fatty acids essentially become the preferred fuel source under those conditions, but they have to be metabolized by mitochondria in the cell. So this requires oxidative phosphorylation. All right. So just real quick, ketosis is not at all the same as ketoacidosis. And I know that they rhyme and they sound very similar, but they really have nothing much to do with each other. Ketosis is a normal physiological state that we all have evolved to be in and out of, and has many beneficial consequences, whereas of course ketoacidosis is a devastating pathological condition that occurs primarily in type 1 diabetics. So, all right, so what about a mouse that you only feed once a day? And you can look at this in a calorimeter. It doesn't matter how this works, but you can essentially tell whether a mouse is burning carbs on a whole body level or whether it's burning fat. So if the level is high, it's burning carbs. And if you feed the mouse, you can see the top line there. The mouse starts burning carbs exclusively until the food is gone. And the glycogen reserves are gone, and then the mouse will crash into ketosis, and for the remainder of the 24-hour period, it will burn fat. And then you feed it again, it goes back up again, goes back down, and you can repeat this for the entire duration of the mouse's life, and in fact they live longer that way and have a better health span. What we had done in this paper is we took different animal models of PKD, a rat model, a mouse model, even cats with polycystic kidney disease, subjected them to different dietary interventions that all induce ketosis one way or another. In this case, we did time-restricted feeding, ketogenic diets, or even acute fasting, and even just supplementing with the ketone beta-hydroxybutyrate. And I'm not going to show all the data, but essentially all the data led us to the same conclusion that really the metabolic state of ketosis appears to be the commonality there. So this experiment shows a time-restricted feeding experiment. So the rats in this case are have access to food for only 8 hours in a 24-hour period, and that's compared then to the control that has ad libitum 24-hour access to the regular rodent chow. And you can see the black dots versus the red dots, a very strong beneficial effect on disease progression by just simply looking at 2 kidney to body weight ratio, or by looking at cystic area. And in fact, we looked at all kinds of different parameters, signaling pathways, fibrosis, and so on, and everything was very dramatically improved. So another way of influencing ketosis is by putting animals on what's called a ketogenic diet. So it's a high-fat, very low carbohydrate diet. And this is shown by the bottom orange line. So you can essentially force an animal to be in ketosis 24/7, for its entire life. And if you do this, or just let me just real quick say what a ketogenic diet really is. In a non-ketogenic diet, like a high-carb diet, such as a standard American diet, also called the SAD diet, is a very high carbohydrate diet, where typically over 50% of the energy comes from carbohydrates. And in a ketogenic diet, you essentially flip this around. You make fats the main energy source, you limit the carbohydrates, and you keep protein about the same. So you don't actually touch protein. And quick myth buster. So when people hear ketogenic diets, they automatically think, oh, that's a high protein diet. So that's not what I'm talking about. So there are some ketogenic diets that are high protein diets, but that's not the classical ketogenic diet. So here we're not actually changing protein. All right, so if we do this, again, there was a very dramatic beneficial effect. So the disease essentially hardly progressed at all in those rats. And again, we can look at all kinds of different parameters here. And then what we also found is that a ketogenic diet actually reverses PKD in this animal model. It doesn't only stop or halt the disease progression, but we can start out with older animals that are at a certain disease burden already, put them on a ketogenic diet and see what happens, after, I believe, 4 weeks in this case. And you can see maybe on the left bottom graph that the total kidney mass actually decreases, whereas the total body mass actually still increases. Cystic area goes down, and everything actually improves to a state that is better to where it was at 8-week-old animals. Okay, ooh, geez, I'm not doing anything. What happened? Sorry. Okay, apologize. Well, let me just go back a whole bunch. Okay, I'm giving away the show here. All right. Okay. Where are we? Oh, too bad. All my jokes are already given away. All right. Good. So another crazy experiment that I wouldn't have thought works is what happens if we just supplement these animals with exogenous ketone, with the exogenous ketone beta-hydroxybutyrate in the drinking water. I would never have thought this works. But strangely enough, this mimicked the effects of ketogenic diets. And you can maybe see the very strong effect here on 2 kidney to body weight ratio, the appearance of the kidneys, and all the signaling pathways, fibrosis, and so on that we've looked at. Everything was greatly improved. So by simply adding this exogenous ketone, we appear to be able to mimic many of the effects of dietary interventions. All right, so take-home messages. Dietary ketosis might slow or inhibit the progression of PKD. Exogenous BHB appears to mimic many of these effects. And of course, this could be translated into the clinic by things like time-restricted eating, intermittent fasting, ketogenic diets, which are all very commonly done by many people already, or something like supplementing with beta-hydroxybutyrate. Real quick, so what about ketosis in humans? So as we all know, our genes did not just evolve, yesterday. Our genes evolved over millions of years. And, depending on where you count in the human lineage, maybe say 5 million years or so. And we all evolved actually as, to arrive at this state, like this guy there on the right, to look healthy and be slim, be able to run away from lions and so on. And we actually evolved to be in and out of ketosis all day long, but depending on the luck that a hunter-gatherer has with their hunt. They might eat something or they might not eat something. Their entire family might be in ketosis for a few days or for like months in the winter time. So being metabolically flexible is kind of part of our genetic programming. And we've sort of lost this in the maybe last 50 years or so, maybe in thanks largely to our diet and lifestyle habits, where we're essentially never in ketosis anymore. We never run out of lack in our lack of hunting, because all we have to do is open the fridge and there's our game right there. So epidemics of obesity, metabolic syndrome, and so on are rampant. Diabetes, and all of the consequences that come with it. And one could argue that this is largely due to high carb diets and lifestyles that essentially prevent us from ever emptying our fat reserves. So many of us are not metabolically flexible. And one thing we've looked at in this paper is also in humans, whether the baseline serum glucose levels might correlate with progression in PKD, which it does. Actually a statistically significant progression, and essentially the bottom line is the higher somebody's baseline serum glucose is, the worse their progression of PKD. And again, there's plenty of literature on this. Hyperglycemia and type 2 diabetes have already been found to correlate with faster progression in PKD, and obesity and overweight as well. Okay, so speaking of COVID, so in the earlier part of the session, we talked about, what was the impact of the COVID pandemic on everyone's lives. Us researchers, we were also affected, of course, by the labs being shut down. We couldn't do any animal experiments, and I happened to have a fantastic nephrologist in my lab, Sebastian Strubel, who suddenly had nothing to do. And I said, okay, why don't we do a retrospective case series study, reasoning that PKD is a very common disease, ketogenic diets are very commonly done by many people. What if there were a population of people with PKD that have already done ketogenic diets, and what was the experience? So we did this study, which wouldn't have happened without COVID. And the results were actually quite stunning and surprising to me. So we were able to recruit about 131 patients here that had all experimented with different forms of ketogenic diets or time-restricted diets. And of course, and so they were all interviewed with a long questionnaire, phone interviews. We gathered their data from their, the health data, medical data. So a strong effect, of course, as one would expect on body weight. So many of the obese patients became overweight. Many of the overweight became normal weight. Nobody became underweight. The average duration was about 6 months that people had been on those ketogenic diets in the study. On the left, to my surprise, about 86% of patients reported that the dietary intervention either strongly or somewhat improved their overall health and well-being. So I always think, when do 86% of Americans agree on anything? So in this case, they seem to agree on something. And the parts of their health and well-being that improved includes many of the typical symptoms in PKD. Pain levels went down, fatigue, abdominal fullness, acid reflux, and so on. So what about some harder data, blood pressure results? Surprisingly, or maybe not surprisingly, because ketogenic diets have already been shown to have a very strong beneficial effect on hypertension, and that's exactly what these patients experience as well. Strong improvements there. And even just plain EGFR values actually improved, strangely enough. So even to a degree that it was statistically significant. And of course, there are many caveats here. So these are self-reported data, and those are self-selected patients, so there can be a lot of biases and so on. So this is definitely not the end-all be-all study, but at least it gave us confidence that patients don't just drop dead like flies from doing this, right? So everything kind of pointed in a good direction. So what about a prospective study? We've actually done, and really Roman Müller in Cologne has done this study. So we just helped kind of with the design of the study, which was funded by the PKD Foundation. It's a prospective, randomized, controlled study, short-term, so more of a pilot study with 63 patients that were randomized into 3 arms, ketogenic diet versus intermittent fasting versus control. And really looking at endpoints such as feasibility, tolerability, but also secondarily looking at hard endpoints, metabolic readouts, of course, body mass index, but also EGFR, total kidney volume. The study has just finished. It's still embargoed, will be presented at the ASN in just a couple of weeks in Florida. But just to the punchline, I think, is that the results all point in the right direction, where actually I would say the effect sizes were actually much, to my surprise, much better than I would have hoped for. So soon this will be published. All right. Let's see. All right. So let's go back to our scheme here. So in the cloud of metabolic disease that are potentially worsening factors for a PKD progression, we can add inputs like high carb diets, avoidance of ketosis, overweight and obesity, metabolic syndrome, type 2 diabetes, chronic systemic inflammation. They're all kind of like, accelerate the metabolic disease cloud up there. And things to potentially do about it are, low carbohydrate diets, nutritional ketosis, exogenous BHB, weight loss. That might be mitigating factors here. All right, so I'm almost done. Real quick, so what if we combine keto and citrate, right? So we combine those 2 clouds and address them all at the same time. Of course, obviously, we can do this in animals. So I'd shown you before that adding citrate to the drinking water was highly beneficial. Adding beta-hydroxybutyrate to the drinking water was highly beneficial. What if we combine them, which we did here, and we were actually able to show a synergistic effect that allowed us to reduce the dose of both of these compounds in this sort of combination here, and have the full beneficial effect, with much lower doses. So that's not published yet, but there's a lot of additional mechanistic stuff in this manuscript that's almost done. So let's see, where are we? Here we go. All right. So we actually ended up launching a company because, as you probably know, dietary interventions are not something that the pharmaceutical industry is interested in or would be able to, fund or do anything with. And a group of just fantastic PKD researchers and actually patients, lots of patients and industry professionals with PKD came together to just try to make something happen. And we put this company together, launched a product, and full disclosure, as I said, I'm the president, so don't believe anything I'm saying. So we came up with this formulation of what's called a medical food called KetoCitra. And here's the composition of it. It's a mixture of exogenous ketone with citrate in a blend of potassium, calcium, and magnesium to make it sodium free. And actually part of the reason to even do all this is because a lot of patients were starting to ask questions and were saying, hey, which BHB supplement should I take? And I always say, take none of them because they're all not meant to be kidney safe. They typically are very high sodium and have all kinds of additives and fillers and so on. So we wanted to come up with something that we can, formulate to be kidney safe. And it's been out on the markets for almost a year now. And that's all right. Here we go. Just real quick to lead into the next talk, we've worked with a group of fantastic dietitians, renal dietitians led by Jessiana Saville, to come up with a sort of like a more comprehensive dietary intervention program for PKD. That is sort of combines a ketogenic diet and sort of with a plant-focused diet, avoidance of these renal stressors such as oxalate, phosphate, and uric acid precursors, combining it with this medical food KetoCitra. This program has been out and about. We've actually published a paper already on a beta test, so that's available, that summarizes all the details about the program and the sort of the first qualitative experiences of a group of about 24 patients with PKD that went through it. By now, it's been, I think, over 100 PKD patients that have gone through this program, with, I would say, really some really stunning successes and fantastic testimonials that they've given us. Lots of people see pain level improvements, improvements in hypertension, and so on. And we're using this program as essentially the training phase in a couple of clinical trials that we're planning, including with right here in Toronto with Dr. Pei. The plan is to have 40 patients on the intervention and 40 controls. And in parallel, we'll do a trial with Dr. Shikio Horie in Japan, in Tokyo, with about 100 patients and 100 controls, following them up for a year to look at the long-term outcomes. I think that's all I wanted to say, and I'll hand things over and I hope I didn't go too much over time, so my apologies for that. Great, thank you very much.
So thank you, Thomas. Before I introduce the next speaker who is going to talk to you about this integrated dietary program, I thought I would just mention a couple of things that I'm a nephrologist and doctor, so we have a somewhat more slightly conservative view because many times a promising experimental study may not work in human. And that's why we want to partner with Thomas to test his program as an independent kind of source to see if we could generate like a similar type of data. And we were very fortunate that Dr. Sujio Huri from Japan that was actually doing intermittent fasting himself and was very keen and want to collaborate on this. So this is a new project that is not yet been launched. We're still going through REB, which is taking a bit longer, but we hope that we will be able to do that probably next year, like maybe early spring, you think? Yeah. So that's the background that I